Hi, today we are looking at motion along a line in 1D, so we'll be utilizing what we've learned in calculus so far to look at movement. So in our workbook, our position is given by ST, so that's our position of an object moving along a line at a time t. Now if we want our displacement over a specific time period, so for example from time A to time B, that would just be S of B minus S of A, which would be our change in position of that object or particle in that time span from time A to time B. For position versus time graphs, our average velocity would be the slope of our secant line. So that'd be our overall displacement over time, or change in S over change in T, or we can write that as our S at B minus our S at A over B minus A. So this is essentially our y2 minus y1 over x2 minus x1 equation. Now, our velocity at a given time is the slope of our tangent line. So our velocity at t is equal to our derivative of s with respect to t, or limit as h goes to 0 of s of t plus h minus s of t over h, which is s prime of t. Now, if we instead have a velocity versus time graph, our average acceleration would once again be a slope of a secant line. So anytime we have an average something, it's going to be a slope of a secant line. So that'd be our overall change in velocity over time is change in velocity over change in time, which would be our velocity at B minus velocity at A over B minus A. So once again, that's essentially our y2 minus y1 over x2 minus x1. Now our acceleration at a particular time is our slope of our tangent line. So that's going to be our derivative of our velocity with respect to time, or limit as h goes to 0 of our velocity at t plus h minus our velocity at t over h, or v prime t. Now, if our acceleration is our derivative of velocity, and our velocity is our derivative of location, then our acceleration is our second derivative of our location. Now, if we refer to speed, we're not worrying about a positive or negative, so it's just the absolute value of our derivative of our location, or absolute value of our velocity. So we have an example. Ball is thrown directly upwards with an initial velocity of 25 meters per second from the top of a building 15 meters tall. The position in meters of a ball above the ground after t seconds is given by a function st equals negative 5t squared plus 25t plus 15. We want to find several things with this. We want to find the ball's displacement in a time from 0 to 2 seconds. We want to find our average velocity from 0 to 2 seconds. Find the ball's velocity and acceleration functions. Find the ball's position, velocity, and acceleration when time is 3 seconds. And how long does it take to reach its maximum height? And we want to know what that height is. Okay, so for part A, we want to find the ball's displacement from t0 to t2. So for that, we're just utilizing the equation they gave us. So we've got st is equal to negative 5t squared plus 25t plus 15. So at t0, that's just going to be s of 0 is equal to negative 5 times 0 squared plus 25 times 0 plus 15. So we know at a time of 0, it is a height of 15 meters. we're also looking at a time of 2, so we'll also look at s of 2, which would be -5 times 2 squared plus 25 times 2 plus 15, which gives us 45 meters. So a time of 2 seconds, it is a height of 45 meters. So that would be our two displacements, but we want to know our displacement from this time to this time. So to get our displacement during that time, we're just going to go s of 2 minus s of 0. So that would be 45 minus 15, giving us 30 meters that has gone up in that time. Now, part B was find average velocity from a time of 0 to a time of 2. So our average velocity is just going to be s of 2 minus s of 0 over 2 minus 0. Now we already calculated s of 2 minus s of 0. We know that that's 30 meters. Now 2 minus 0 would be 2 seconds. So our average velocity over that time would be 15 meters per second. Part C is find the ball's velocity and acceleration functions. So we know our velocity is just going to be s prime t. So our first derivative of this function. So if we take the derivative of this function, we get -10t plus 25, where we know our acceleration function is just our derivative of our velocity function. So if we take the derivative of this, we get -10. Okay, D was find a position, velocity, and acceleration at a time of 3 seconds. So we've got S of t is equal to -5 times t squared plus 25 t plus 15. We'll substitute in a time of 3 seconds. So we've got -5 times 3 squared plus 25 times 3 plus 15. So at a time of 3 seconds, we are at a height of 45 meters. Now our velocity at that time, we'll use our -10t plus 25. So velocity at 3 seconds would be -10 times 3 plus 25, which gives us -5 meters per second. Let's look at our acceleration at that time. So we know our acceleration at that time would be simply -10. So if we have a time of 3, that's -10 meters per second squared. Okay, our next question is how long does it take to reach its maximum height? Now, we know the object is going up and then coming back down. So at its maximum height, it's going to be changing from a positive velocity to a negative velocity. So at its maximum height, its velocity will be zero. So we can say we have our max height when Vt equals zero. So if we so we're going to take our equation for our velocity, which was negative 10t plus 25, and we'll make this equal to zero. So we've got zero is equal to negative 10 times t plus 25. We'll move the 10 to the other side. So that gives us 10t equals 25. Divide both sides by 10, and that gives us t is 2.5 seconds. So we know our max height occurs at a time of 2.5 seconds. Now to figure out what that height is, we'll take our position equation. So s at t is equal to negative 5 times t squared plus 25t plus 15, and we will substitute in our 2.5 seconds. So we've got negative 5 times 2.5 squared plus 25 times 2.5 plus 15. So that gives us s of 2.5 is equal to 46.25 meters. Okay, so next we're going to look at some motion notation. If our s is greater than zero, the object or particle is going to be on the positive s-axis. If it's less than zero, we're on the negative x-axis. If our v is greater than zero, the particle is moving in a positive direction. If our v is less than zero, the particle is moving in a negative direction. If our v is equal to zero, then that means our particle is at rest. Now, if our sign of v is changing, that means our particle is changing direction as it moves. If our a is greater than zero and v is greater than zero, or a is less than zero and v is less than zero, our speed is increasing. So if you recall, our speed doesn't depend on direction. If our a is greater than zero and v is less than zero, or a is less than zero and v is greater than zero, then our speed is decreasing. So we're just going to have this velocity time curve, and we're going to rate what's happening to our speed during this and rate it to how we were breaking up our graphs earlier in this chapter. So I'm just going to add some dashed lines to this. We're going to split any place have a maximum up anywhere we cross our x-axis. Any place we have a minimum. And then we're going to use some notation we've already been using. Now, we're going to link what we've been using to what we just covered on that previous page. So if we have this velocity time curve, we can see if our velocity is zero and we're going upwards, that must mean our velocity is speeding up. Now, if we look at it from a velocity and acceleration, we can see that our velocity was positive here. And our acceleration, if we take the derivative or our tangent line anywhere on the slope, we get positive. So if we have both velocity and acceleration being positive, that matches what we had on the previous page where it was speeding up. Now here we can see that we are slowing down because our velocity is getting closer to zero. We can see our velocity is still positive because it's above our axis. But if we take a tangent line anywhere here, we get negative. So if these are opposite signs, we have something slowing down. Now we can see we're going into negative velocities and we're getting more negative. So this is speeding up. It's just speeding up in a negative direction. And we can see that our velocity is below the axis, so therefore velocity is negative. And if we take a tangent line anywhere of this, we also get negative slope. So once again, if these are both the same sign, it's speeding up. This one here, we're going back to zero, so we're slowing down. We can see our line is below our axis, so we know our velocity is negative, but a tangent line anywhere on here is going to give us a positive slope. So once again, if these are opposite signs, you're slowing down. If they're same signs, you're speeding up. Okay, so we're going to look at an example. A particle is moving along a horizontal line. Its position as a function of time is given by st equals 2t cubed minus 21t squared plus 60t, where t is equal or greater than 0, and our t is in seconds and s is in meters. We want to find our velocity and acceleration functions. We want to find at what time does the particle change direction, during what time intervals is the velocity increasing, and during which intervals is the speed decreasing, and find the total distance traveled during the first 4 seconds. Okay, so first thing is finding our velocity and acceleration function. So we know our velocity at t is equal to our derivative of s at t. So that would be 6t squared minus 42t plus 60. Now we know our acceleration at t is equal to our derivative of our velocity at t. So that would be 12t minus 42. Okay, so that's part A. Part B, at what time does a particle change direction? So for this, we are going to find our critical points. So that would be where our velocity is equal to 0. And then we'll put those on a number line and look at where velocity is positive and negative and see where it changes direction. So we want to make this equal to 0. So we've got 0 is equal to 6t squared minus 42t plus 60. Now we're going to take the 6 out because everything here is a multiple of 6. So we've got 6 times t squared minus 7t plus 10. And then we'll product sum factor this. So we've got 0 is equal to 6 times t minus 5 and t minus 2. So that gives us critical points when t is 5 and when t is 2. Okay, so we know at a time of 2, our velocity is 0. At time of 5, our velocity is 0. We'll then figure out if e- if this section is positive or negative velocity, if this is positive or negative velocity, or this is positive or negative velocity. So if I put a number that's less than 2 into here, so for example, if I was to plug 1 in, I would have a positive times a negative, so that's going to give us a positive. So we know that from our starting time of 0 to 2, we're going to have a positive velocity. Next, we can pick something between 2 and 5. So for example, flee, if I was to put flee into here, we have a positive times a negative times a positive. So that's going to give us a negative. So between 2 and 5 seconds, we're going to have a negative velocity. And then if we choose something larger than 5, let's say 6, we would have a positive times a positive times a positive. So we would have a positive velocity here. So we can see that it changes direction at a time of 2 seconds and a time of 5 seconds. Now we need to do this because we could in some cases have our velocity just pause briefly at that time and then continue in the same direction it was going before. So we can say change in direction at t equals 2 and 5. Now, we want to know during what time intervals is the velocity increasing. So in other words, when is our acceleration greater than 0? So we're going to look at our acceleration equation, and we are going to find when it is equal to 0. So we'll plug 0 in for acceleration, and we know that equals 12t minus 42. Now I would move the 42 to the other side. We've got 42 equals 12t. Divide both sides by 12. Now we get an upper location to put on this plot, and that would be 3.5 is equal to our t. So we know that that would be here. Now this whole section would still stay all negative, but now we've got sections for acceleration. We know acceleration at 3.5 is 0. So now I would just take this function and plug in something less than 3.5. So for example, if I was to plug in 2, that gives me a negative. So we know everything over here is a negative. Now on this side, I can plug in anything greater than 3.5. So for example, if I plugged in 5, that's going to give me a positive. So we know our acceleration in this domain is positive. So we can see that we have it accelerating in a positive direction anytime our time is greater than 3.5. Now our next part, D, was during which intervals is the speed decreasing. So if you recall, our speed is decreasing if our velocity and acceleration have opposite signs. So we can see we have opposite signs here. So we can say that it's decreasing from 0 to 2 seconds. We also see opposite signs here, so between 3.5 and 5 seconds. Now, E is our total distance traveled. So our distance traveled isn't the same as what is our change in displacement. So what we're going to do is look at how far we travel while we're going in one direction, and then how far we're traveling while going in another direction. So we can see that it changes direction at a time of 2 seconds. So we are going to start out with our formula. So we've got S of t, or S at t, is equal to 2t cubed minus 21t squared plus 60t. And first 4 seconds, so that gives us a starting point of 0 seconds. So we've got S of 0 is equal to 2 times 0 cubed minus 21 times 0 squared plus 60 times 0. Now that just gives us a distance of 0 meters. So it's starting at 0 meters. Then we'll look at how far it travels while it's going in a positive direction. So we're going to look at S of 2. So that would be 2 times 2 cubed minus 21 times 2 squared plus 60 times 2. So that gives us S of 2 is equal to 52 meters. Next, we're going to look at the end of 4 seconds, which is between here while it's all going negative, because it's going negative from 2 to 5. So it's going to be the same direction from going from 2 to 4. So we're going to look at S of 2, or sorry, S of 4. So that's going to be 2 times 4 cubed minus 21 times 4 squared plus 60 times 4. And that gives us 32 meters. So we can see that between these two, we traveled 52 meters. And then we went 52 meters to 32 meters, so that'd be 20 meters. So our total distance traveled would be 52 plus 20, giving us 72 meters total.